Okay, so let's get to the bottom of the topic essentially. So we have a generic linear ODE. The right hand side is no longer delta of t, but it's just any function f of t. We will do typical applications or examples later, but let's provide the general method first. So the only difference is that I want to use convolution at some point at the end of the problem. And again, in the beginning, we're going to focus just when the initial conditions are 0. When they're not 0, there's just a little modification, but the main idea is the same. You will see in examples. But for now, again, focus on this particular initial value problem. Linear, non-homogeneous, starting with 0 initial conditions. So we do that by applying the Laplace transform first. So take the Laplace on left side, just like before. And on the right-hand side is Laplace of f of t. So just because the reason we said before in the previous part, this ends up being the characteristic polynomial in S. So again, if it's not clear, just watch that previous part again. But exactly because these are 0, when you distribute the Laplace transform, the left side ends up being a s squared big Y plus bs big Y plus cy, and Laplace of little f of t, let's call it big F of s. You will see that the beauty of this method with the Laplace with the convolutions is that you don't actually have to find this Laplace transform at the end, that's in fact the cool part of the method. So to find y, we're going to pull out y from the left side. And big Y, pay attention here, becomes 1 over as squared plus bs plus c times big F of s. So really pay attention here and make connection with the previous example when we use the impulse function on the right hand side. So what's the difference when you compute big Y? If f of t was delta t, so if it was just the impulse function at time 0, then big Y was just this. It would not multiply with anything, just 1 over as squared plus bs plus c. So big Y would have been just the transfer function, because remember that was denoted by big H of s, also known as the transfer function. Now, when you have another function f of t instead of delta of t, as it turns out, big Y ends up being just the product of the transfer function and the Laplace of f of t. Very standard format, right? I mean, delta of t, big Y becomes h of s. A different function, big Y becomes h of s times f of s. So then what's the solution of the ODE? Well, the solution is the inverse Laplace of this. But this is where using the convolution makes things much easier. So little y of t will be the inverse of big Y of s, which is inverse of big H of s times big F of s. But what do we know about the main property of convolution? Well, we know that we can distribute the inverse operator over these factors and put the convolution between them. So this is where the main advantage lies, because what's the inverse of big F of s? That's going to be f of t. So I can actually bypass finding big F of s, because I know that the solution of the ODE is nothing but the inverse of big H, which remember in the previous part we denoted by little h of t. So that's just simply the convolution between little h of t and whatever you have on the right hand side of the ODE. So what you have to compute in fact is just the inverse Laplace of the transfer function. Once you do that, the solution is the convolution between that, the inverse of the transfer function, and the right hand side. So you bypass finding the Laplace of the right hand side, which is actually cool if you don't have a formula for the Laplace of little f of t. So remember from the previous part, this is called the impulse response. And you'll see with some examples how easy it becomes. So again, if you accept the solution in the form of a convolution, if the problem says that you should do that, all you got to do is to set up the transfer function. So essentially the mechanics of the problem is setting up h of s, which is 1 over s squared plus bs plus c, then finding the inverse of that, and then convolution between that and the right hand side. So there are essentially just 3 main steps in writing the solution of the ODE. Again, provided that it starts from 0. If it doesn't start from 0, you'll see an expression like this, but some additional other stuff, some other terms besides that. So finally, I think we're ready now for a couple of examples. We're going to have another part just with examples. So let's do one which is, let's see, not too difficult to compute. Again, have the Laplace table in front of you. So suppose I want to solve y double prime plus 9y equals cosine of t, and let's start from 0. Y prime of 0 equals 0. Okay, so it fits the framework, right? Linear, starting from 0, and I want to solve it via convolution. The first thing to do is set up the transfer function, look at the characteristic polynomial, that's going to be just s squared plus 9, find the impulse response. So again, transfer function, the impulse response is the inverse of the transfer function. Here that goes with the sign. Remember, you have to multiply by 3 so that you can fit it with the table. 3 over s squared plus 9, that's going to be 1/3 sine of 3t. And that's the impulse response. What is the solution of the ODE? Well, the solution would be the impulse response that you just found, convolution, the right hand side of the function, cosine of t, and you're done. I think this is really nice. Again, I hope you appreciate it if you take the effort to understand it. And in fact, the main conclusion of the section in the book is written in I think it's the nicest, one of the nicest conclusions in the book, essentially, because it emphasizes the efficiency and the advantageous format of writing it with convolutions, because then you can provide like a theorem of solving any type of differential equations that fits this framework. So the remark sounds kind of like this: the solution of a linear initial value problem with 0 initial conditions is the convolution between the impulse response at time 0 and the forcing term. F of t, right? I mean, which is denoted by f of t in the way we denote typically a linear ODE. So in a nutshell, basically describe a way to solve any linear ODE that starts from 0 initial conditions. So the solution is always the convolution between impulse response and whatever you have on the right hand side. So you will see in the last part of the lecture that follows from here. Another cool part of it is that since the solution only depends on the, since the impulse response is the same, you could actually solve a multitude of differential equations with the same left side, but by changing just f of t. So let's say, for example, I have a system, a mass spring system, in which I apply various types of forces, but the left side is the same, you know, same damping, same the mass, same spring constant. You do the impulse function, you do the impulse response once for all, and then the solutions will simply replace f of t in this part, right? I mean, later on, if you change f of t from cosine of t to, let's say, tangent of t, you only change this part because this guy stays the same. The impulse response will be the same because it comes from the left side. I mean, the left side of the system, which will remain the same. So we're going to go over several more examples in the last part. Stay tuned.